Hello again, physics friends. Today we're going to talk about Newton's second law and 2D polar coordinates. In particular, by Newton's second law, what I mean is the acceleration being equal to 1 over m times the net force on an object. In other words, acceleration is brought about by a net force. It's not equal to the force, but it's equal to the force divided by the inertial mass of the object in question. Now, this is a vector equation, and so it's really hiding within it multiple equations, one for each dimension of the problem. And in Cartesian coordinates for 2D motion, we could write this, we could break this single equation into two, one for the x acceleration and one for the y acceleration. For 2D polar coordinates, we would also break this equation up, but instead of x and y, we would use the r hat and phi hat directions. But before we do that, let me just give this another name, ax and ay, meaning the acceleration in the x direction and the acceleration in the y direction. So in 2D polar, we would be looking for the acceleration in the radial and tangential directions. And the radial acceleration would be 1 over m times the net force in the radial direction. And the tangential acceleration would be 1 over m times the net force, and you guessed it, the tangential direction. Now from our previous videos, we know something about a sub r and a sub phi. We know a sub r is r double dot minus r phi dot squared. And we know that a sub phi is equal to r phi double dot plus 2 r dot phi dot. And you recall that's just breaking out the acceleration vector that we derived in the previous video, which had a radial component and a tangential component. Okay. So let's expand these two equations using our information for the radial and tangential components. The first equation here is going to give us r double dot minus r phi dot squared is equal to 1 over m times the net radial force. And the second equation is going to give us r phi double dot plus 2r dot phi dot, that's this piece here, is going to equal 1 over m times the net force in the angular direction. And we can see something important immediately. In contrast to Cartesian coordinates, in which the x acceleration only involved derivatives of x, not derivatives of y, look at the so-called radial equation. I mean, it is the radial equation in 2D polar. It involves phi dot terms. And look at the phi equation, the tangential equation. It involves r dot. So we have coupled differential equations. So solving this set of equations in general can be challenging, but let's do a few examples in which we're kind of going to restrict ourselves so that not all four of these terms are present. And we'll start with the pendulum. And in particular, as drawn here, we're going to have a planar pendulum, meaning that the pendulum can swing in the plane of the page, but it never comes out of the page or into the page. So this example is characterized by a constant distance from the origin, meaning the length of the string is constant. In this case, it's capital R, but phi varies. And what are we trying to find? We seek a solution for phi as a function of time. Okay, that's what we are trying to solve. So what we're learning here in the Newton's law equation is we need to know the net force in each of the two directions, the radial and the tangential directions. So let's see, let's first define those two directions. We have the r hat, or radial direction, and then the phi hat vector points in the direction of increasing phi. So phi hat points toward increasing phi. So that's why the phi hat points up and to the right and not down and to the left. Okay, well, let's do a force diagram for the bob. Draw a little loop around the object of interest. I'll represent it by a point, and we'll draw the forces that are present here. We do have a tension force by the string on the pendulum bob, and we do have a force of gravity, like so. And our goal is to break these forces up into their components in the r hat and phi hat directions. Okay, so what we can see is that tension is a purely radial force. It has no tangential component, but the gravitational force has components in both the phi hat and r hat directions. Okay, so again, this direction is the phi hat direction. This direction is the r hat direction. And so let's actually write out the tension and the gravitational force. All right, so here we can write the tension is equal to the magnitude of the tension in the minus r hat direction. And how about the force of gravity? Okay, we have two components. We have in the radial direction, mg times the cosine of the angle phi. How do I know it's the cosine? Well, this angle and this angle are the same. And so the radial component of FG will be mg times the cosine. Whereas the tangential component will have a magnitude mg times the sine of phi. Okay, so we can write this now as plus mg cosine phi in the r hat direction, and then the phi hat component, the tangential component of the gravitational force, points in the minus phi hat direction. So we're going to have minus mg sine phi in the phi hat direction. So now I've copied down Newton's second law in the radial and tangential directions, and let's focus on the tangential direction because we seek, remember, where our goal is to find phi of t, the angle. And we have some information, which is because r is a constant, it's equal to r, capital R, that tells us that r dot and r double dot are both 0. So what that means is the second term on the left-hand side is gone. Okay, and then we also need to know what is this net force in the phi direction. Well, that's the term that we already identified in the phi hat direction for FG. Okay, so because there's no phi hat component to the tension. Okay, so now we have, taking this equation, we have capital R times phi double dot is equal to 1 over m times the force in the phi direction, mg sine of phi with a minus sign. My masses cancel. I can rearrange things a little bit to find phi double dot is equal to minus g over r times the sine of phi. This is the equation of motion that will tell us, if we solve that differential equation, that will tell us how phi evolves in time. Okay, turns out that that is a hard problem to solve, but we can make the approximation for small angles that sine of phi is approximately phi, and that will allow us to solve this problem. So let's see a little bit more about that. In particular, we can see as a math aside here that if you plot the function sine of x and the function y equals x, that those two functions are very similar at small values of x, whereas they're different at higher values of x. So the approximation sine x approximately x is a good approximation for small angles, small values of x. How small? Well, it doesn't have to be that small, actually. Consider the following. 30 degrees. At 30 degrees, the sine of 30 is 1/2, 0.5, and 30 degrees in radians is pi over 6, or 0.52. So even at 30 degrees, the approximation is very good of thinking about sine of x as x. Okay, so if you make that approximation, then you can change a nonlinear differential equation because phi appears in a nonlinear function, sine of phi. You can approximate it as a linear differential equation, phi double dot equals minus g over r phi, meaning the second derivative of angle with respect to time gives you back that function with a minus sign. So we know something about those solutions. We know they're periodic, and so we can solve this and write it as something. Well, there's many different ways to write it, but they're equivalent. We could say a times the sine of omega t plus b times the cosine of omega t. And what is this omega? Well, omega is defined to be the square root of g divided by the length of the string. And you can see why that is, because when you take two time derivatives of this quantity, you'll get back an omega squared out front, and the omega squared has to be g over r. So let's do another example, this time one in which r varies, but phi is constant. Okay, for our next example, let's allow r to vary, but phi be constant. So you can almost imagine like a roller coaster track or some rigid track, and we have an object, a car or a bead, that's forced to drive along that track. So the angle with respect to the horizontal never changes, but the position along the track can change. So we could put, for example, we could put an origin here. So the bead is allowed to move away or towards the origin. Well, we could do this in radial coordinates, but it really ends up just being a Cartesian problem. It's a rectilinear motion. But let's see why this is. So let's consider the radial equation here. For Newton's second law, we have r double dot minus r phi dot squared is equal to 1 over m times the net force in the radial direction. But if phi is constant, that tells us that phi dot is 0. So the second term on the left-hand side is gone, and we are just left with r double dot is equal to 1 over m times the net force in the r direction. But that looks a whole lot like x double dot is equal to 1 over m times the net force in the x direction. And indeed, in the limiting case where the angle doesn't change, and r is the only thing that can vary, that is rectilinear motion. So you'd expect the form of Newton's second law in polar coordinates to look identical to what it does in Cartesian coordinates. So we don't have much more to say about that problem. But let's move on to a third example. All right, this time we're going to let r vary, and we're going to let phi dot be constant. And we can call phi dot omega. Okay, so using the same idea as before, we could come up with a scenario in which we have, say, a bead that's allowed to travel along a stick, and also the stick is rotating at a constant rate. So this entire stick and ball system is rotating at a constant omega, where omega is phi dot. Okay, we can ignore friction, and let's say that this is like a top view. So we're looking down, say, on a tabletop, and on the tabletop we have this stick that's rotating with a bead on it. And so from this perspective, gravity points into the page. Well, the next thing we can do is make use of Newton's laws. And in particular, we don't have to figure out what phi as a function of t is. We already know that because omega is a constant. So we don't need to do much work to figure that out, right? We know d phi dt is a constant, which we're calling omega. If that's true, then we know phi of t is a linear function of time, which is the starting position plus that angular velocity times t, omega t. What we really want to do is find r of t. And how do we find r of t? Well, we focus on the radial equation. All right, so we have Newton's second law in the radial direction, which is r double dot minus r phi dot squared is equal to 1 over m times the net force. In the radial direction. Well, what is the net force in the radial direction? If I look at this bead, nothing is pushing it along the rod either direction. There's maybe a normal force, though there is a normal force by the rod on the bead, but that normal force has to be perpendicular to the rod. So that would be in the phi hat direction, but there's no radial force. So actually in this problem, F net in the radial direction is 0. So what does that tell us? R double dot is equal to R omega squared. Right, so we're taking this term, setting it equal to 0. We get R double dot is equal to R phi dot squared, but phi dot is omega. Okay. So once again, we have an equation, a differential equation, in which the second derivative gives you back the original equation. Gives you back the original function with an overall scaling factor out front. Okay, so we seek a function whose second derivative gives you that original function. Well, we know, you probably recognize that that is an exponential. So how about we guess the following? Let's let r of t equal e to the at. In that case, r dot is a e to the at, and r double dot is a squared e to the at. So that all looks good, right? We have r double dot is equal to a constant squared times a position as a function of time. So that works. And in fact, this position as a function of time, e to the at, is r of t. So we can rewrite this as a squared r of t. So we come full circle. Is that the only solution? No. And there's another solution, which is when you have a minus sign up top. The first derivative changes sign because you'll get minus a e to the at, but when you head to the second derivative, that will cancel the minus sign, e to the minus at. When you take the second derivative, the minus sign up front is canceled, and you're left with a squared times r of t. So either approach is fine. They're both, in general, part of the solution. The first term tells us that the bead will move further and further away from the origin at an exponentially increasing rate. And the other equation is telling us that there's a chance the bead will actually get closer and closer to the origin. So in general, we need both of these. Well, let's think about the limiting case of time going to infinity. Okay, so we think about putting a bead on the wire and starting the wire to rotate and then waiting a long time to see what happens. Okay. Well, we do know that as time increases, these exponentials will change, and in particular, the second one will fade to 0, and the first one will become by far the dominant term. Okay, so limiting case as t goes to infinity, we're going to find that r of t is only the first piece. Because b e to the minus omega t, that term goes to 0 as t goes to infinity. Okay, so let's then go back to the original equation that was our solution r of t, and let's assume that we pick a scenario where the object starts at rest at a given location. And let's try to make a graph of what that will look like. All right, so we have two things going on. We have this exponential decay, which would look like this, okay, on the one hand. Then on the other hand, we have a function that's growing with time exponentially. So that'll look something like this. Okay, and the total function will be the sum of those two. So we'd start up here at r naught, and at large time, when the green function has faded away, we're basically going to be hugging the purple curve. And then we transition from r naught up to the purple curve, like so. A little bit tricky to draw. Right. Okay. You might be wondering why this is r over 2 and this is r. Well, that we can show an initial condition aside. If v starts at 0 and r starts at r naught, then we know r naught. Then we know that r of t equals 0 is going to be a e to the 0 plus b e to the 0, which is a plus b. And then v of t is r dot, which is omega a e to the omega t minus omega b e to the minus omega t. So the velocity at t equals 0 would be omega times a minus b. And if that's 0, then we must have a and b being equal to each other, number 1. And number 2, a plus b has to equal r naught. So that tells us that a is the same as b is the same as half of r naught. So by looking at this function, the position is a function of time, we can see the bead eventually is going to fly off of the rod, unless you have an infinitely long rod. But the bead starts sliding away from the origin, and then it slides faster and faster and faster as it goes. Is there any scenario in which the bead will not get shot off of the stick or off of the rod? Well, I can think of one easy one, which is put the bead at the origin at the start. Okay, if r naught is 0, then that tells us that a equals b equals 0, and we just have the position being 0 for all time. So, okay, in that case, the bead stays on, but that's kind of an extreme case. The other way you can keep the bead on the string, or on the stick rather, is by getting rid of this purple curve, right? If the only curve is the green one, then the bead will stay on the stick. It won't go arbitrarily far away from the origin. So what does it mean to get rid of this purple curve? Well, we have to set a to 0. So is there a set of initial conditions that give a equals 0? Because if so, then the bead will not fly off of the stick. Right, so our task is to make the bead stay on the stick, which means in general, the only way that that's going to happen is either you put the bead at the origin, in which case r is always 0, or you figure out a way to make a 0 so that there's no exponential growth of the position, only an exponential decay of the position. So how can we make a equal to 0? Well, we can look at our initial conditions, right? Remember that r at t equals 0 is a plus b, and v at t equals 0 is omega times a minus b. We solved this already, okay? And we want a equals 0. Okay, so from our position equation, if we set a to 0, from our position initial condition, we see that r naught has to start off, or b rather, is equal to r naught. From our velocity equation, we see that v naught is equal to omega b. Well, actually, there is a minus sign in there, so v naught is equal to minus omega b. Now, we can combine these two outcomes to show that v naught has to be equal to minus r naught times omega. Okay, so we're going to start at some position r naught, and the velocity will be inwards. And if you pick the velocity just right, the initial velocity just right, so it's equal in magnitude to the initial position times omega, if you do that, then the position as a function of time will be b e to the minus omega t, because a is 0 and b is r naught. Very good. And then the velocity would look like v of t is equal to derivative of r, which is minus omega b, e to the minus omega t, and b again is r naught. Okay, so what this is saying is that the position is getting smaller and smaller with time, but so too is the velocity. So we can make a plot of this case, time and r of t, and this time we only have one function, and that is we start at some position r naught and we decay towards the origin. So the bead will always approach the origin, it will never leave the stick. Okay, so in sum, we have an expression for the acceleration in the radial and phi directions. We've used that in conjunction with Newton's second law to find equations of motion for purely angular motion, purely radial motion, and then in this case, a combination of both radial and angular motion. So hopefully these examples have been a little bit illuminating as to how to do Newton's laws and do physics in 2D polar coordinates. And we will wrap up there. So until next time, take care and be well.